Okay, we're going to try this example here, and so you have to use your imagination a little bit with me. So let's imagine that we have a boat that's docked out at the sea, and that we were able to measure on a particular day its low tide and its high tide and the times that they corresponded with. So let's provide you some given information. We know that high tide on that particular day is 13 feet, and low tide is at 5 feet. We know that low tide occurs at 4 a.m. in the morning, or 4 hours past midnight. And then we know that high tide occurs at 10 a.m. or 10 hours plus midnight. So given that information, we want to go ahead and model the periodic function of the tides on that particular day. So the graph that we have is we have our y equals our a times sine quantity bx minus c plus d. So we have an opportunity to remember what all those particular modifications to our sine function do. A was amplitude, B helped us with our period, C was a little bit about our phase shift, and D was our vertical or horizontal or vertical lifting or sinking. So let's start to plug in some information, and then let's work for the remaining pieces that we have. Amplitude. Well, to find our amplitude, we kind of need to get a sense of where's our middle part of our graph at. So we know that we have a minimum at 5 feet and a maximum at 13 feet. And we kind of can see that with this particular graph there. We know that its middle point, or its natural position, is halfway between the two, which is here at, was at 5, 13 minus 5, it's 8, add 4, so this looks like about 9 feet. So we would say then that its graph right there is at 9 feet at its normal position, or 9 feet above sea level. So we're going to say that its rise, or its D, is 9 feet. Continuing on from here, its amplitude is from its normal position to its maximum or its minimum, so it changes by 4 feet. So I have an amplitude of 4 feet. All right, those were some of the low-hanging fruit. So let's go ahead and try to figure out what its period is. Well, this period tells us that every 12 hours is when the tide goes in and out. So we have a period of 12 hours. Given that, that's going to help us discover what this B is. So 12 equals 2 pi over B. Switch those around, and I get a B equals pi 6. So now our B, or our period factor there helps us with a pi over 6. Now we need to figure out what our phase shift is. So to help us determine what our phase shift is, let's look at our phase shift equals our C over our B. Our B that we know right now we have, and our phase shift occurs right here is where does our graph basically start at? And if our graph starts right there, right at normal tide, and its time at that particular point is 7 p.m. or 7 a.m. Halfway between 4 and 10 is the halfway point between our low tide and our high tide. So we're going to use this point as kind of the beginning point of our graph, and that tells us it's occurring 7 hours after midnight. So our phase shift is 7. So 7 equals our C, which we do not know, divided by our B, which is pi over 6. So C in this case equals 7 times pi over 6. Using some algebra, we have all of our variables now, so we can plug them in. So this graph is modeled by A is 4 times sine. My B value is pi over 6 x minus my C value. My C value was 7 pi over 6 plus its vertical dimension, which was a 9. So this particular sine function, given our initial parameters that we're modeling on a particular day, high tide and low tide, which is occurring at very specific times, we can model that tide function by that particular graph.